Hello everyone. In this lecture we will discuss functions. So let us start with some examples of relations so that we can understand the difference between a relation and a function. Suppose we have a set of students say s equal to s1, s2, s3 and another set of marks in mathematics say m 70, 75, 85 and 90. Now we can define a relationship between these two sets indicating the student and their marks. Now suppose we have three relations R1, R2 and R3. Now is any of these three relations is a special type of relation? Special in the sense, suppose I wish to know the marks of student S1. So can I get the marks of student S1 from these relations? Now check R1. In R1 look at this S1 related to 70 and again S1 related to 75. It means here S1 is related to 70, S1 is related to 75. So though it is a relation, but through this relation we cannot get exact marks of S1 because two different ordered pairs are there in which S1 is there. Now look at this R2 S1 related to 75. So this is the only ordered pair where S1 is there. So from this you can say the marks of S1 is 75. Now here the marks of S1 and S2 are given, but you don't know, you cannot find the marks of S3. So but here in R2 look at this, you can find the marks of S1, S2 and S3. So look at this R2 is a special type of relation. In R1 you have some confusion about the marks of S1 and in R3 you cannot get the marks of S3, but in R2 you can get the marks of each of the student and no such confusion is there. That's why this is a particular a special type of relation. It has some two additional properties. The two properties are one, for each of this element, uh, one element is defined from M, and for all these elements S1, S2 and S3, some of the elements is there, means no element is left without an element from set M. So in this way this is different from these two, and we will say this type of relation as a function. Function means for each of these element, some element is defined in another set and each element has a unique element defined in. So in simple term we can define a function as, let x and y be two non-empty sets. A function f from the set x to the set y is a rule that assigns each element of x a unique element of y. So you can define simple just like as a rule. Anytime suppose you define from y to x, suppose a function is there and you define function f x equal to x square. It means this is a function. Whatever value you assign to x, you will get a square of this function. So basically it is a rule that assigns each element of x a unique element of x. So this is the definition of function. Now domain and range of functions. Suppose this is a set x and suppose this set is y and a function is defined from x to y. Say this is the function f. So this set x is known as domain and the set y is known as codomain, and those elements which are mapping of some of the elements of x. For example, suppose this x1, x2, x3 and suppose xn elements are there, and for each of the element mapping is defined. Suppose this is for x2 and suppose for x3 and suppose for xn. Similarly, mapping of each of these elements is defined. So this set, it may be possible that some elements are left without any mapping. So these sets in which mapping is defined means the elements of y corresponding to the elements of x, those elements who have mapping in y. This set is known as range. This set is known as range. For example, look at this. Suppose 1, 2, 3. This is the set X, and suppose another set is 2, 3, 4 and 5, and suppose the mapping is fx equal to x plus 1. So 1 is the image of 1 is 2, 2 is 3, 3 is 4. So 5 is the element which is without any mapping. So this 1, 2, 3, this set is domain, this set is domain, and this completes it. This is x domain, this y completes it 2, 3, 4, 5. This x equal to 1, 2, 3, y equal to 2, 3, 4 and 5. This is codomain, and range equal to 2, 3, 4. So in this way you can define domain and range of a function. Now here we have defined the set x and y. In some of the cases we define a function as a formula. For example, if I define y equal to x square. So in this way, in this function, I have to find the domain and range. So look at this, how can I find the domain and range in this case when only formula is given to you? Generally, whenever we talk about domain and range, we talk about real line. So the domain is the set of values of x for which this function is defined, or you can say for which value of y exists. Now you have to check all those values from real line for which y has some value. Now look at this is x square. If you assign all real numbers, for every real numbers you will find value of y. So domain of this set is minus infinity to infinity, or you can say x belongs to R. Now look at this. If you have to find the range means the values of y. Domain means the values of x for which this function exists or for which y has some value. The range is the values of y for these values of x over the domain. So now look at this. If you assign minus infinity to infinity x, the values between this interval minus infinity to infinity, then what kind of values you will get for y? This is x square. X square means for all negative numbers you will get a positive number. So it means you will get only non-negative values of y. So you can write y is greater than equal to 0, or you can write it y belongs to 0 in closed interval infinity. So this is the range. This is range of this function. Similarly, just take another example. Say for example y equal to under root 1 minus x. Take this example. Now look at this. Y equal to under root 1 minus x, and you know under root x, this 1 minus x, this must be greater than or equal to 0, or in simple term you can say this is a non-negative number, because under root is not defined for negative number, otherwise it will be a complex number. So we are talking about real line. So 1 minus x, this must be greater than equal to 0. So we have to check the condition for which this function will exist. So the condition is 1 minus x must be greater than equal to 0, or you can say x is less than equal to 1. Put x in right hand side, then you will get x is less than equal to 1. So the domain of this function is domain of this function is x is less than equal to 1, or you can say x belongs to minus infinity to 1, and this is closed interval because this is equal to 1 is equal to. Okay, now what about the range of this function? Now again look at this. If 1 minus x is greater than equal to 0, it means this is greater than equal to 0. Now always you will get a positive value of y. So the minimum value will be 0 and all other are positive numbers. So you can write range as y belongs to, or simple terms you can write y is greater than equal to 0, or you can write y belongs to, or other words you can write y belongs to 0 to infinity. So in this way you can define domain and range of the functions which are given in the form of formula. You can take another functions and just try to find the domain and range of the functions. Now types of functions. One function. A function is said to be 1 1 or 1 to 1 if each element of x, suppose the function is from x to y, if each element in x has a distinct image in y. Means every element, say suppose two elements are there, x1 x2, so both have distinct elements here in y, y1 and y2. So if every element has a distinct image in y, then you will say the function is 1 1 function. So this is the definition only. How can we write it mathematically? So to write it mathematically, suppose we say let f is a function from x to y. Then f is said to be 1 to 1 if fx1 equal to fx2, then this tautologically implies x1 equal to x2. The meaning of this one is, look at this. Suppose the mapping of 2 is the same, suppose x1 and x2. Look at this, fx1 equal to fx2. So fx1 equal to fx2. If the mapping of two different x1 and x2 is same, then these two must be same. It means if x1 is equal to x2, then every element will have distinct image. So if mapping of 2 is same, it means the two elements are also same. So mathematically we can define a function in this way, or alternatively we can say if x1 is not equal to x2, if x1 is different from x2, then fx1 is also not equal to fx2. So both are same. So either you can start with this fx1 equal to fx2 and you can show x1 equal to x2, or you can start with x1 is not equal to x2, then fx1 is not equal to fx2. Let's take one example. Suppose say f is a function from R to R, a set of real numbers to real number defined as fx equal to say x plus 3, x plus 3. Now we have to show that this is 1 1 function. So write it 2x plus 3. Then we have to show the function fx is a 1 to 1 function. So what we will do, we will assume two elements of R. Let x1 comma x2 belongs to R such that fx1 equal to fx2, fx1 equal to fx2. So we'll start with this condition and we have to prove that this condition is also true. So this is assumption and this is what we have to prove true. So fx1 equal to fx2. Now fx1 equal to fx2, fx1 equal to fx2, this implies 2x1 plus 3 equal to 2x2 plus 3. So this implies 3 will cancel out, 2x1 equal to 2x2, and finally this will give you x1 equal to x2. So in this way we have started with this definition and we have proved that x1 equal to x2. So you can say the function is 1 1 function. Now many one function. Many one function means suppose this mapping is x to y, this is x to y. So many one means if elements of x1 have same image in y, you can say two or more than two elements, say two or more than two elements in x have same image in y. Say this is y1, x1 and x2. Then we say this function is many one function. So for this, what we have to show, we can say f is a function from x to y. If for two different values x1 and x2 belongs to x, fx1 equal to fx2, then you will say the function is many-one function. Now, for example, look at this. Suppose f is a function from R to R plus, from R to R plus, and defined as R plus union say 0. So defined as fx equal to say x square, fx equal to x square. So show that this function is many-one function. So many-one function means we have to show that x1, x2 for two different values, fx1 equal to fx2. So you can give example of any two values. For example, let minus 2 and 2 belongs to R. Minus 2 and 2 belongs to R. So we can say that f minus 2 equal to 4 and this equal to f2. So these two elements are different. X1 is not equal to x2 but fx1 equal to fx2. So here in this definition, look at the x1, x2 different values were there. Here you can write is x1 is not equal to x2. This logically implies x1 equal to fx1 equal to fx2. So here we have proved that minus 2 and 2 are different, but f minus 2 equal to f2. So in this way you can say this function is many-one function. So for this function you have to be very cautious about these two values R to R. In case you define R plus to R plus, here you are defined from R means now you can choose negative number also. But if you choose R plus to R plus, then you cannot write minus 2. In this case it will not a many-one function. So be cautious while you defining many-one or one-one. You have to be careful about all these two sets from where to where this function is defined. Now on to function. Suppose we have a set x, another set y. Suppose this set is x and this is y, and f is a function from x to y. Now function f is said to be onto if for each element of y, say suppose this is y is the element of y. For each element of y, there exists some element in x so that fx equal to y. It means y is the image of x. So for each of these elements, if there exists some elements in x such that these elements are the image of the elements of x, then you will say mapping is onto. It means in simple term you can say no element is left without any image or mapping in y. So if no element is left without image in y, then you will say the mapping is onto mapping. Now to prove that a function is onto function, what you have to do? So you have to select an arbitrary element, say y or k, any point, arbitrary point. Then you have to show for this element there exists an element x in capital X so that the mapping of x is in y. So in this way you can prove that a function is onto function. Now look at this example. Again we will take, suppose f is a function from R to R defined as fx equal to twice x plus 3. Now we have to show that this function is onto function. So how can we show? So we can write let k belongs to R. We are just assuming, suppose y equal to k. There is an arbitrary element of this set and this set is here R. So we are assuming let k belongs to R, be an arbitrary element, be an arbitrary element. Now we have to show for this element k there exists some element in this set. Here this set is R, so that the mapping of this is in k. So how can we find the element of here in this set R so that the mapping of this element is in k? So put k fx equal to k, because look at this is fx. So put here, just do some rough work, put fx equal to k. So you will get 2x plus 3 equal to k, and from there you can write 2x equal to k minus 3 and x equal to k minus 3 by 2. Now check this value k minus 3 by 2. You know k belongs to R. K belongs to R because k is the element of R. Now we have to check whether this x k minus 3 by 2 is a member of R or not. If k is a real number, then definitely k minus 3 by 2 will be a real number. It means for each element k, there exists an element k minus 3 by 2 such that the mapping of this element is in k. So we have completed first part only. So this is the rough work, or you can do it fair work also. So you will find x equal to k minus 3. If you write fx equal to k, then you will find x equal to k minus 3 by 2. So you can write, after doing this calculation and checking that x equal to k minus 3 by 2 belongs to R, then you can write for each k belongs to R, there exists an element k minus 3 by 2 belongs to R such that such that now we'll apply the definition of f in k minus 3 by 2, and we will show that the mapping of k minus 3 by 2 is in k. So how can we show? So apply this mapping here. So f k minus 3 by 2, you know fx is 2x plus 3. This is x. So you can write twice into k minus 3 by 2 plus 3. So this equal to 2 will cancel out, k minus 3 plus 3, and this is finally k. So now we have shown that for each k belongs to R, there exists an element k minus 3 by 2 belongs to R such that mapping of k minus 3 by 2 is in k. Now since k is an arbitrary element, you can say every element in Y is the image of sum of the element of x. So in this way, you can prove that a function is an onto function. Now identity function, a function from x to x, and we denote it by ix. A function from x to x is called identity function if it is defined as x equal to x, means the mapping of x is in x. So suppose for example, x equal to 1, 2, 3. So if we define a function fx equal to x, so this is an identity function, means mapping of each element is in itself. So this is known as identity function. Now constant functions. Suppose we have two sets, one is x and another is y. This is y. If the mapping of all elements in x is in the same element of y, means this is a fixed element, or you can say constant, then you will say the function is constant. So how can we define? Suppose f is a function from x to y, and the function is called constant function if fx equal to say c, means for all values of x, mapping is in c, which is a constant, say c, here x1, x2, x3. So this is a constant function. So this is the basic concept of functions. So I hope that you got the concept of one on to many one, and these identity and constant functions.